Laser space weathering of carbon. What can we expect from NEO sample return?
So you advanced it.
Okay. Thank you. Right. Hi, thank you. So today I'm going to be talking about some new data that I've been taking with Jeffrey Gillis Davis at the University of Hawaii. So the big picture is here. This spacecraft, OSIRIS-REx, is going to rendezvous with the asteroid Bennu, and in about 9 years return pristine regolith samples from an asteroid, a near-Earth asteroid. And what we want to know is how much does space weathering affect meteorite samples, and does space weathering affect our ability to characterize these samples once they're returned and we want to study them? Because the first thing that we will do when we get these samples back is want to do a petrologic study so we can understand what the samples are. And the first way to do this is just texturally to look at the mineral relationships. And then there are more fine-scale techniques such as Raman spectroscopy, which is what we talked about today, and then other spectroscopic techniques. So if space weathering alters the Raman spectrum too much, then our calibration for determining, say, the petrologic type of the asteroid or the meteorite might be invalid. So just a quick review of the classification of meteorites. We have chondrites, and they're split up into carbonaceous chondrites, ordinary, RK, and enstatite. And then these asteroids, or asteroid types, spectral types, correlate with the meteorite classification. So these S-type asteroids are most of the ordinary chondrites and enstatite chondrites. And then the darker asteroids are C-type, so they're corresponding to the carbonaceous ones. And then those are further subdivided into B-type asteroids, which are what OSIRIS-REx and Hayabusa 2 plan on targeting. And these could be the CI, CM, and CR because type Bs tend to have more evidence for hydrated minerals. And then these are also further subdivided into petrologic type, which have these numbers 1 to 6. So numbers that are 1, 2, and 3 indicate that there had been aqueous alteration, with 3 being the most pristine. And then type 3 to 6 is thermometamorphism, where, again, 3 is the most pristine, and then 6 is most altered. Okay, so we're going to be talking about Raman spectra. So Raman, you might not be familiar with, but it's basically a vibrational spectrum technique. And it's very good at differentiating between polymorphs, so it's very good for studying carbon. There's a lot of different types of carbon phases. So starting here at the bottom, we have a spectrum of graphite, and there's one peak here, and we call this the G band for graphite. And then nanocrystalline graphite, you also get this D band peak, so D for disorder. These 3 spectra in the center are for macromolecular carbon that we find in meteorite samples. So macromolecular carbon isn't quite like graphite, but have a very similar spectrum. So we have the D and G bands for CV, CM, and CR, and as you go up on this graph, the macromolecular carbon gets more disordered, and we know this because the peaks get wider and the ratio between the peak heights changes. The CM and CR also have these fluorescence features, which add slope to the spectrum, but unlike reflectance spectra, the slope doesn't actually change our interpretation. The important thing about Raman is just the peak positions, their intensities, and their peak widths. And then we have these 2 amorphous types of carbon up here. So we have glassy carbon, which peaks are almost indistinguishable, and then amorphous carbon glass, where D and G band completely go away, and you're left with just 1 peak. So if you thermally metamorphose these things, you start to go down on this graph towards graphite. Okay, so if you know information such as the D band width, you can correlate them with some known parameter like peak metamorphic temperature and make these sort of models such as this one. It's just one example of a model, but if the space weathering again changes the Raman spectrum too much, then this trend is not going to work when we want to characterize our samples. Okay, so space weathering, this has been seen this already today. Basically, we're doing laser space weathering, which only models the micrometeorite impact part. We get vaporization, but we don't produce agglutinants, nor do we simulate any sort of shock-induced heating. But we do get the vaporization and deposition part. So, so we're simulating impact energies for near-Earth objects at 1 AU, which have a 16 kilometer per second projectile speed, and so there's a flux of about 1,300 joules per square centimeter per million years. And so the laser just is simulating that part where you're imparting an amount of heat. And so we have a kind of a low shot energy density, so we have a high time resolution. So this is our setup. We have a very large laser here, which gets focused down into our vacuum chamber, and then the sample sits here, and this sample cup gets hit. So we have samples so far we've tested uncompressed graphite and Allende, which is a CV3 meteorite powers, and then a thick section of Murchison, which is a CM2 chondrite. And we are using a Raman microscope with small laser spot size. Okay, so our preliminary results for graphite, start here at the bottom again with an unweathered graphite with a single G-band peak. And then you weather it for 10 minutes in our chamber, and we start to see a D-band. Then after 20 minutes, the peaks are almost undistinguishable. And then we measured the side of the carbon, or the side of the sample holder, which was covered with this black stuff, which has that spectrum. So this is essentially this classical disordering of the graphite, and it's being caused by our space weathering experiment. So we start here with unweathered, then the blue is nanocrystalline, and then we get to the two top ones are the amorphous. So they get more amorphous as you go up. And you can use the information that you get from the peak heights and widths to figure out basically what the carbon coordination is. So down here, graphite is purely sp2 or 3-coordinate carbon. You weather a little bit and nothing, that doesn't change very much, but this 20-minute one is called glassy carbon, and it has only 20% tetrahedral carbon, but it's again amorphous, and then the vapor deposit is mostly tetrahedral, but again amorphous. So space weathering goes up on this ternary diagram. It's pretty simple, but the meteorite samples have this macromolecular carbon, which we know isn't really like graphite. And interestingly, the Allende powder, unweathered here at the top, and then after 5 minutes of weathering, despite the fact that the sample gets darker and redder in reflectance, there's no change. And then after 40 minutes, there's a significant amount of darkening, but still the Raman spectra doesn't change, which is interesting. You'd expect that there would be some correlation between the reflectance and the Raman. So we thought maybe this has to do with something experimental. So we took a slab of Murchison, shown here, just a picture, and then we shot just in one place to try to concentrate the space weathered particles. And in fact, in some of these craters, which I point out with arrows, we found some melt glass. And so this is zoomed in here, and there's two blobs of melted glass. And the spectrum, which has some pyroxene, olivine peaks, and then this interesting feature here at 1600 wave numbers. So I zoomed in to that spectrum, into this feature, and then comparing with Murchison again, like for the lower number of shots, and then comparing that to this glassy carbon spectrum from our graphite space weathered sample. And again, ignore the slope because it's the position and the peak width that are important. And this feature is very similar spectrally to this feature. So we're pretty sure that in Murchison, in these glasses, we've formed glassy carbon. So we've altered the carbon phase, organic carbon phase, into glassy carbon. Okay, so conclusions is that we know about meteorites from the meteorite collection that there's thermal metamorphism, and that changes the macromolecular carbon to such as narrowing the Raman bands, and so it's turning it into carbonized and then eventually graphite. But we're showing that at least the micrometeorite impacts part component of space weathering is actually increasing order, so it's the opposite of thermal metamorphism. Now, other people have also found glassy carbon in a few meteorite samples, including Murchison, and this was mentioned by both Huseman and King et al., but the King et al. Paper is interesting because they did isotopic studies and they actually ruled out a lot of different theories about the origin of these glassy carbons. And some of the theories were either it's like a pre-solar, protosolar source. Actually, Fischer-Tropsch type reactions were an idea, but he was able to rule it out because there isn't an internal nanophase iron inside the glassy carbon, so there's not really a good reason why FTT or Fischer-Tropsch type reactions would explain them. They have a very typical isotopic values for the solar system, so they're not from pre-solar sources. So I think we're the first people to suggest that micrometeorites could be the impact origin is a origin for this glassy carbon. It's also kind of strange to me that Murchison, we found abundant amounts of this glassy carbon in the Raman spectra, but didn't see anything in Allende, despite the fact that they both have kind of a glass that you can see optically. So that might just because that Allende has glassy carbon, but it's below the detection limit of the Raman. Or it might be stemming from a difference between the macromolecular carbon. Macromolecular carbon is not very totally well understood, so this could be the case that because Murchison has experienced some aqueous alteration, it might be easier for it to become glassy carbon in a space weathered environment. So there's a lot of future work to be done. The first thing that we're going to do is take fib sections of these glass melt blobs and then try to actually confirm that we have glassy carbon by spectroscopy in a TEM, and then perform many more experiments on the rest of the carbonaceous chondrites, and then follow up in the way future with shock impact studies to try to understand what shock adds to this equation. And that's it.
Thanks. Tim Glotch, Stony Brook. I think this is really cool and important too. I was wondering if you could provide me with a conversion factor to go from your 10 minutes of space weathering experiment in the chamber to millions of years exposure in space.
Yeah, it turns out to be kind of a hard thing to answer because it's 10 minutes on a powder, so you're not really imparting as much energy as you think you are. But we sort of calculated it earlier. I just go back to the right thing. So if it's just if you're just adding the energy up 7.5 millijoules per square centimeter, then that many shots at 20 hertz gives a million years. So it's something like that divided by 20 hertz divided by 60. Right.
A suggestion for why you don't see this thing in Allende is that Allende has precious little carbon compared to Murchison. It's about half a weight percent rather than 2.5 or 3 weight percent. So you're starting with a lot less material.
True, but we can still detect the very intense macromolecular peaks in Raman. So if 1% is converted, then we should still be able to see something, some change, probably.
Yeah, Larry Taylor, University of Tennessee. What was the size of what was the footprint of your Raman spectra, of your, the point?
It depends, but we were using 10 micron spot sizes, so much smaller.
Yeah, I would suggest, you can go down much finer with micro Raman, that you're getting a combination of a whole bunch of stuff that's really making it more difficult to interpret.
Yeah.
And if you get down to the fine grain size, get down to a fine micro Raman spot, you'll be able to discern different phases there and maybe get better signals.
True, thanks.
Yeah, I was wondering, you mentioned you saw some large visible changes without a lot of changes in the Raman. If you're going to follow up on that and, maybe, one idea would maybe be that you're producing little kind of nanophase carbon blebs in a similar to the iron.
Yeah, that's why we really need to get to do the TEM work so that we can see if there are nanophase iron, we can see that in the TEM.